This is group 9 of the IDL project. We're proposing multi-pose fusion, single-view 3D reconstruction using diffusion models with the flexible camera pose. So 3D reconstruction is one of the fundamental challenges in computer vision with the different applications in robotics, autonomous vehicles, gaming, VR, etc. There are so many approaches such as traditional methods, structure for motion, multi-view, stereo vision, neural networks methods such as NF, voxel-based, point cloud, and mesh reconstruction. All these, which they have the caveat of that they need multi-view images, and also they have like so many ambiguity about the camera extrinsic and intrinsics. What if we just have like single view image that we want to reconstruct the image with? Use the generative AI models such as diffusion models that have been already pre-trained on billions of image and text pairs, and they have like a great prior to be able to generate novel 2D images. Why not just train the diffusion model on 3D models? Because we don't have the enough large data set, and also the computationally very expensive. So we generate multi-views with the diffusion models and then feed these multi-views to the 3D reconstruction pipelines. The default models, they use this pipeline to feed the diffusion models with the input embeddings of the 2D image to generate the multi-views in the different angles and elevations, and then reconstruct them with the NERF or other approaches to get the 3D output object. But the challenge that all face is the inconsistency with the different multi-views that they've been generating. And to combat this, basically they try to fix the elevation and constrain the camera poses to be able to have like more consistent generated outputs, which that cause more constraint on the camera poses, and then 3D reconstruction would be poorer. So we're trying to enhance this multi-view synthesis with the flexible camera poses. Is 3D CAD objects datasets from Observerse and Google Scan objects for the test dataset, and we rendered a subset from this massive dataset, which is 20K rendered objects. And for the test dataset to be able to match with the baseline, that they only use 3D objects from Google Scan. Synchromers to combat this multi-view inconsistency issues, they use this 3D CNN to be able to get a spatial volume and then like feature map to the fossil volume, and then they use depth-wise attention, this 3D aware depth-wise attention, to be able to condition it on the diffusion model denoiser, and they train on the 800,000 objects of the Optoverse and 800 GPU hours, which is massive. And also, like as I said, they fix the elevation angle of all the target and input images to the 30 degrees. So to have like more consistent, and this delta V that we see is like a difference angles between the target and input images that they feed to the unit, and unit has been frozen because it's not trainable. The results from the synchromers, as you can see, this is with 30 degrees elevation and it's pretty consistent and good. But as we train this with the 50 degrees and 70 degrees, you can see that the inconsistency is horrible, and this sofa doesn't even look like a sofa anymore. And our approach is using epipolar attention and plucker embedding as an embedding positional embedding. Epipolar attention has been used to mask the attentions for each corresponding feature to the epipolar line pixels. So it just shows attention to pixels throughout that epipolar line between different target views. And plucker embedding has been used to show the attention only to the same ray direction of the other object. So the front face of the doll only shows attention to the front face of the doll in this image. And we fine-tune this in a new attention networks, and along with our 3D CNN attention from the synchromers and the 20,000 object of the changes we made. The epipolar attention plucker embeddings that have been like concatenated to the cross attention here, and then we have like now flexible camera poses with minus 10 to 30 to minus 30 to 60 degrees, and then our dataset also has like a random poses and it's not fixed. As for result, as you can see, synchromers, our baseline for elevation of 70 degrees is very inconsistent in the generative views, but ours is very way better, although we haven't fine-tuned for so many epochs and our dataset is way smaller. For reconstructed result with the 3D reconstruction methods news. Our evaluation metrics are based on two approaches. One is the metrics for the novel view synthesis. Basically, is like PSNR and it's similarity metrics and signal to noise ratio between the generated target images and also with the prediction. And we have a matrix for the single view 3D reconstruction, which is a chamfer distance and volume IOU. Basically, check the similarity between the 3D reconstructed objects. As I said, since the evaluation takes a lot of time, we just have like 30 objects on the evaluation to match the paper results, and our average currently is very similar, as you can see, to the paper results, although we just fine-tuned on 20,000 subset of the objects. And these are the metrics for the 3D reconstruction. For our challenges and future work, our challenges is like this. The whole pipeline is very computationally expensive. The data collection, the model training, and the 3D reconstruction evaluation. And for the future work, we use like a larger training dataset, larger training epochs, and also adding gradient accumulation because our batch sizes are very small due to the memory constraints. And we're going to fine tune on the objects embedded with the background. Listen.